Betelgeuse is a red giant star so immense that if it replaced our Sun, it would stretch out past Jupiter's orbit. It's enormous, highly unstable, and on the verge of colossal explosion. These explosions rank among the most powerful bursts of radio energy in the entire universe, releasing more energy than 1 billion suns combined. Are we ready for what's coming? Betelgeuse, a massive red supergiant and one of the closest stars to Earth, recently underwent a dramatic dimming that captured global attention and sparked much speculation. This unusual behavior has led astronomers and the public to wonder about its possible implications. Some scientists think this could signal an impending supernova, a catastrophic event when a star runs out of nuclear fuel, collapses under its own gravity, and explodes spectacularly. Such an explosion could have serious consequences, stirring concern both in the scientific community and among the public about what impact it might have on Earth. Located prominently in the constellation Orion, known for its distinctive shape and bright stars, Betelgeuse, also called Alpha Orionis, is the brightest and largest star in this constellation. Data from NASA's Hubble Space Telescope and other observatories revealed that in 2009, Betelgeuse experienced a massive ejection of material. This event is unprecedented for a star of its kind and has fascinated astronomers worldwide. While our Sun regularly has coronal mass ejections, Betelgeuse's 2009 event was unique and offers new insights into the life cycles of massive stars. The exact distance to Betelgeuse remains debated, with estimates ranging widely, some suggesting it lies about 724 light-years away. Measuring distances to red supergiants is notoriously difficult due to their size and complex properties. Betelgeuse shines roughly 100,000 times brighter than the Sun, making it one of the most luminous stars visible in our night sky. But this immense brightness comes at a cost. Betelgeuse burns through its nuclear fuel rapidly, speeding up the inevitable end of its life. When it finally runs out, it will collapse and likely explode in a supernova, possibly forming a neutron star or even a black hole. This leads to an important question. Could Betelgeuse pose a threat to Earth? If a supernova happened within a few tens of light years, the effects could be catastrophic. A supernova can release light rivaling that of an entire galaxy, so even though Betelgeuse is relatively distant, such an explosion could have significant consequences. The last supernova observed in our Milky Way occurred centuries ago, but the notable supernova in 1987, located 169,000 light-years away in the Large Magellanic Cloud, showed us the potential scale of such cosmic events, though it posed no direct threat to Earth. The danger zone around a typical supernova is a serious consideration, especially regarding its ability to disrupt life on nearby planets. Yet, supernovae pale in comparison to gamma-ray bursts, which are far more powerful and dangerous. Supernovae can devastate planets, stripping away ozone layers that shield life from harmful solar radiation, leaving ecosystems exposed to lethal UV rays. Recent studies highlight new risks from massive stars ending their lives explosively, with supernovae producing some of the universe's brightest phenomena, sometimes outshining entire galaxies. If Betelgeuse exploded, it would become the second brightest object in our sky after the Sun, visible even during the day, casting shadows with its intense light, a breathtaking yet terrifying cosmic display. However, the visible light is only a fraction of the energy released. The more concerning threat comes from the high-energy radiation, X-rays and gamma rays, that can severely damage Earth's protective ozone layer, potentially triggering mass extinctions. In the moments following a supernova, intense radiation poses immediate dangers, but cosmic rays emitted afterward can persist for centuries, continuing to bombard Earth with lethal particles. Interestingly, traces of iron-60, a radioactive isotope created in supernovae, have been found in ocean sediments and lunar soil, suggesting Earth was impacted by such events millions of years ago. Currently, astronomers believe no nearby stars pose an immediate supernova threat, but ongoing research reveals new dangers from particular supernovae that emit extreme X-ray radiation. These occur when a dying star is surrounded by a massive disk of material, which, when struck by the supernova's shock wave, heats up and emits high-energy X-rays over vast distances. Such supernovae could have a planet's ozone layer up to 150 light-years away, potentially triggering extinction events. Thankfully, no such X-ray supernova candidates are close to Earth now. These findings refine our understanding of the galactic habitable zone, the region where conditions support life, showing it's shaped not only by star formation, but also by the threat of deadly radiation from stellar explosions. Frequent supernova explosions in certain regions can irradiate the surrounding space, increasing risks for any potential life forms there. New research suggests that the inner edge of the galactic habitable zone lies farther from the galactic core than previously believed, reshaping our understanding of where life might thrive. So, what will the Betelgeuse supernova look like from Earth? While it's reassuring that Earth's biosphere will likely remain safe, the event itself will be impossible to miss. Experts predict Betelgeuse will shine brightly for over 3 months after the explosion, reaching a luminosity about half that of the moon, roughly 9 times dimmer than a full moon. Essentially, it will appear as a brilliant point of light in the sky, visible even during the day, casting shadows at night and captivating anyone who looks up. This cosmic spectacle will fascinate people worldwide, remaining visible to the naked eye for several years as its remnants gradually fade. As scientists continue studying Betelgeuse, they gain deeper insight into the life cycles of massive stars and the explosive processes that mark their end. During a supernova, not only is light emitted, but heavy elements like gold, silver, and uranium are also forged under the immense heat and pressure, a process called nucleosynthesis. This process enriches the interstellar medium with the essential building blocks for future stars and planets. Interestingly, the leftover debris, known as a supernova remnant, can become a stellar nursery where new stars form from the expelled gas and dust. This cyclical nature highlights how the death of one star can give rise to others. Researchers have found supernova remnants still forming stars millions of years after the initial explosion, showcasing the universe's dynamic and interconnected nature. Another fascinating role of supernovae is as cosmic distance markers. Astronomers use Type Ia supernovae, explosions of white dwarf stars that reach consistent peak brightness, as standard candles to measure vast cosmic distances. This technique has been pivotal in understanding the universe's expansion and led to the discovery of dark energy, the mysterious force accelerating this expansion. Supernova studies also provide clues about the habitability of exoplanets. Researchers investigate how radiation from these stellar explosions might impact nearby planets' atmospheres, potentially influencing their capacity to support life. Such research underscores the importance of understanding the cosmic environmental factors shaping life throughout the universe. The possibility of witnessing a nearby supernova also raises intriguing cultural questions. Throughout history, supernovae have inspired myths, legends, and artistic expressions. A star's explosive death is not just a scientific event. It becomes a powerful symbol of transformation, destruction, and rebirth. In many cultures, the sudden appearance of a bright new star in the sky has been seen as an omen or cosmic message. Advancements in technology have revolutionized our ability to detect and study supernovae. Space telescopes equipped with sophisticated sensors capture detailed images and spectra, revealing the composition and behavior of these events. Ground-based observatories play a crucial role in monitoring transient phenomena, allowing astronomers to respond rapidly and gather real-time data. Looking ahead, the future of supernova research is promising. New instruments like the James Webb Space Telescope will offer unprecedented insights into stellar life cycles and the complex dynamics of these extraordinary cosmic explosions. The explosive deaths of stars like Betelgeuse offer valuable insights that could revolutionize our understanding of stellar evolution and the fundamental forces shaping the universe. In essence, studying Betelgeuse and its imminent supernova provides a window into larger themes such as stellar life cycles, cosmic recycling, and the profound influence these events have on both life and culture. Examining massive stars enhances our awareness of the complex and often violent cosmic processes that govern the universe, helping us grasp our place within this vast, ever-evolving cosmos. Supernovae are pivotal moments in the cosmic timeline, marking the death of a star and giving rise to various celestial structures. For example, the remnants of these explosions can form nebulae, immense clouds of gas and dust that become fertile nurseries for new stars. These nebulae often contain complex chemical compounds, which include the organic molecules that are the building blocks of life. Furthermore, The shock waves from supernovae can ignite star formation in nearby molecular clouds, a phenomenon known as triggered star formation. This process highlights how interconnected stellar events are, demonstrating that one star's explosive end can spark the birth of new stars and planetary systems. This underscores the role of supernovae not only as endpoints, but also as catalysts for ongoing cosmic evolution. On a grand scale, supernovae also distribute heavy elements throughout space, enriching the raw material from which future stars and planets form. This enrichment influences the chemical diversity essential for life. Such cosmic recycling emphasizes why understanding supernovae is crucial in astrophysics, particularly in tracing the origins of the elements that compose our planet and ultimately life itself.